So welcome back to the sessions. I am Ramon Canal. I'm from the UPC, the local Polytechnical University. It's my pleasure to chair this session and to introduce first Lars Bergstrom from Google. He will be presenting us the progress and updates on RISC-V based Android. Lars is the Director of Engineering at Google on the Android team. He works on the platform programming languages, including Java, C, C++, and Rust, and the supporting tools and libraries. He's also serving as Google's Corporate Director to RISC-V International and Chair of the Board of Directors of the Rust Foundation. Before Google, he was at Mozilla Research, initially contributing to the Servo browser project and directing the integration of Rust into Firefox and the partner ecosystem. Later, he led Mozilla's AR and VR work, shipping software and building OEM relationships on many different devices. He graduated with his Ph.D. on computer science from the University in Chicago in 2013. So let me welcome Lars on stage. Thank you.
Excellent. Thank you. Thank you, and thanks to the program committee for allowing me to give sort of an update on where we're at with Android on RISC-V, where we're going, and to talk a little bit about a new initiative that we're launching called RISE that's intended to help fund and really further accelerate some of the great community work that's going on around open source software for the RISC-V ecosystem. So, late last year, I came up and said, hey, we've got Android building on RISC-V, and we have a prototype, and I promised to everyone that we were going to bring RISC-V as a Tier 1 supported platform to Android. And so today, I want to be accountable and give you an update and talk through all of the great progress that's been made by our teams, as well as the ecosystem over the last 6 months. Before I jump in, I want to clarify a couple of terms here. Android is the open source operating system itself, whereas AOSP, or the Android Open Source Project, is the open source project that provides access to all of not only the source code, but also all of the tooling and compatibility tests required to build Android, port it to your device, etc. Everything that I'm going to talk about today is freely available as open source. No registration is required to download and use these tools. Now, it does not include things like proprietary firmware blobs. It doesn't include some of the Google mobile suite, like the applications like Gmail and the rest. But it does include everything that you need in order to port the Android operating system to a device or test it out. So unfortunately, I don't have any product announcements for today. I know that's what everybody's looking for. They want to know, hey, when can I have RISC-V eyeglasses running virtual reality or something? Nothing to announce today, but I do have a lot of really great updates to give around the key areas of progress. So the last time I was up at a RISC-V Summit last year, I mentioned that we were trying to move from an early prototype that basically had support for some of the native languages, C++ and Rust, running in sort of a headless Android environment. And I'm really happy to tell you today that we now have the Android runtime available. That means that you can run normal Java and Kotlin applications on the RISC-V environment. We also have an emulator available, so you can now run full graphical demonstrations of Android in an emulated environment to test out all of the new features, all of the languages, and all of the tooling support. We have all of the pre-built tools available as well, so all of the compilers that are targeting RISC-V are now pre-built and available for download as part of the operating system. And one of the big things that we've really focused on over the last 6 months is going from the initial port, which supported RV64GC, and starting to take advantage of a lot of the really innovative new extensions that are coming as part of our either mandatory or optional in the RVA22 profile. So really going in and saying where should we be applying vector optimizations, where should we be looking at using the bitmap operations, and how do we plumb that all the way through the stack, from the emulator, through the kernel, through the compiler and tool chains, and then up to usage within libraries and ultimately applications themselves. We have profiling working, but in the spirit of accountability, I do have to note that we don't have the debugger working right now. We're hoping to have that in the near future. And like I mentioned, the open source contributions are really a huge part of this. So the Android open source project is about 100 million lines of code. Of that, 75 million lines of the code is other open source projects that are not Android. And so really those contributions upstream have been at the heart of a lot of the work that the team has been doing. So when you look at something like the vector or bit manipulation extensions, it's not sufficient for us to just put them in Android, right? We have to work with the QEMU team to make sure that they're exposed at a platform level. We have to work with the kernel team to make sure that they're available, that the registers get cleared when entering user mode, that all of that is working, that LLVM fully supports it and everything is well tested and works with the entire stack, and then work with the upstream maintainers to land optimizations to their libraries that take advantage of these extensions. And that's been a lot of work. We have patches available. Some of them have started landing as well upstream. And I really want to say a big thank you to a lot of the folks, not only on the team, but throughout the ecosystem, many of whom may not have even known that you were benefiting Android with your work in doing your optimization and bringing all of these great contributions across the ecosystem. And of course, you know, the topic of this summit, the work at RISC-V International has been really foundational to all of this support, working with the standards bodies and all of the working groups to make sure that the ABI is ready. That is, that we have standard calling conventions and we have ways of building applications and running them on the operating system that we know are going to sort of stand the test of time. That is, as we add new extensions and new features, that we're going to be able to have them interoperate with operating systems that may have been built on previous versions. And so a big thank you to everybody who's been working in those committees and in those working groups and seen some proposals coming from our teams trying to explain why we had specific needs on those areas. And so, you know, no talk would be complete without a demo. So this is us booting the emulator running fully graphical Android. So again, all of this information and the ability to reproduce all of the demos and all of the work that I'm saying here is fully available online in our public open source projects. You can just build the emulator, run it on top of QEMU today, connect up, and then also test all of your applications and see them. So it does take a little bit of time to boot right now. It currently takes about 8 minutes on a fairly beefy high-end machine to fully boot Android inside of the emulated environment. We're hopeful that over the next 3 months we'll get that down to about 3 minutes. Given that it takes Android about 30 seconds to boot on a normal phone, that's starting to get to the point where people can actively iterate. That is, rebuild the environment, add new features, and test them out in there. So let's see. Let me let it finish showing you the settings dialog, because of course that's why people buy phones, is to get a really good settings experience. So screen there died, but that's okay. I know what's going on. So basically what's happening right now, so I mentioned that it's about 8 minutes. We're basically starting, so I mentioned bringing Android as a tier 1 platform to support for RISC-V as a tier 1 platform to Android. What that means to us is not only having building support, but also CI support, so testing of all of the features. So one of the things that we're doing is standing up additional dedicated hardware to perform all of the continuous testing so that we know that not only did we get all of the tools and libraries working once, but they continue to work. This is one of the biggest challenges in open source software, right? None of these packages, the Linux kernel, LLVM, all of the libraries we use, none of them stay still. They all keep moving, and you always want to pick them up for new features, new security updates, and the rest. And so it's a constant effort to make sure that all of this is working. And then later this year, we're looking to make it possible to be able to run the emulators inside of virtualized environments. So this would mean that you'll be able to test Android inside of cloud environments and check all of that. So let me take a little bit of a dive on some of the areas where we've had to perform some key optimizations, just so you can get a sense of sort of what was really required as we were standing it up. So Bionic is our runtime in Android that provides a lot of the functions that you're familiar with from libc and the rest. And one of the key things that we have to do, that we know we have to do in the platform, is optimize a lot of the really core primitives. So memcopy, memset, all of the string operations, all of the math operations. Even when fully optimized, these can easily be approaching around 1% of workloads. And without vectorized versions of some of the memory operations, we can end up having it take tens of %. And so one of the things that we really want to do with this port is make sure that as we bring up the Android operating system and as people start developing great hardware, that the software is fully ready to take advantage of all of those features. If we have a version of Android that's still using scalar operations to clear memory, we're going to fail at benchmarks, the apps are going to be janky, and so it's really important that as we see these first devices, that from my side, that the software is fully ready to take advantage of all of the new features that are coming. On the rest of the toolchain side, we've really been working, I mentioned about the work upstream at RISC-V International on the ABI, really trying to nail down how is TLS going to work, what are platform reserved registers, what do we think is going to be coming in the space of atomics in the future, and how do we make sure that we're sort of future-proofing everything so that everything is working really well. And I'm proud to say that there's been fantastic progress on that front. Now, it isn't all easy, right? Some of these things are really challenging. Good support, we've started rolling out direct use and hand coding of the vector intrinsics that have been made available so we could optimize some of the libraries. But compiler auto-vectorization support is one of the things that's really mandatory for good performance, not only in benchmarks, though of course benchmarks are important, but also in many of the libraries we use. For example, Skia, one of the graphics libraries that we rely on. And the challenge here is not just that auto-vectorization is hard, which I'm a compiler guy, it's hard, but it's extra hard because there's continued evolution throughout the ecosystem, right? LLVM and GCC are shared tool chains with many targets. There's active optimization work. There are new features on other platforms coming. And so just having the patience as you're working with the open source project and working in a constructive way to make sure that we work on these changes, we have proposals, we work them through the standards committees, through the open source working groups and get them landed. We're looking forward to seeing that, but I do want to own that that's a very hard problem, getting auto-vectorization support in particular in, but it is something that we're investing in and looking forward to. And just to give you a sense of one of the kinds of changes and some of the challenges that we see, so we've been working with a lot of upstream open source libraries, including libping, which is an image processing library that we use on Android. And fortunately, they were totally willing to take our RISC-V patch, as well as the optimization, but part of the feedback from the maintainers was, well, how do I test it, and how do I build it, and how do I know if it actually worked? And so I think that's one thing that I really want to come back to, is how are we helping the rest of our open source ecosystem have access to the same kind of continuous integration and continuous testing that we're doing on Android, so that as they land optimized versions of their libraries, we're able to make sure that they're properly taking advantage of all of the features in the relevant profiles, and that they continue to work over time as new features get added to those libraries. And I mentioned expanding to Java and Kotlin, but of course C, C++, Rust, Java, and Kotlin are not the only languages that run on Android. Dart is another memory-safe garbage-collected language that is also multi-platform, so it runs not only on Android, but also on other operating systems that we won't talk about here. And so they have started working on their own RISC-V port, and they've gotten it running and building command line only applications right now, but they've started the work on Flutter and the rest. And I'm really excited because Dart and Flutter are really widely used across our ecosystem. It's not just a million applications, but it's many of the top applications within the Android ecosystem. And so it's not sufficient for us just to bring Android and the libraries. We also have to bring all of the languages and tools with, so that when our application developers see some of the great RISC-V hardware that's being built by everyone in this room, they're able to bring their applications over easily, port them over, and see them run on all of this hardware. And that brings us, speaking of applications, to sort of the Android ABI. And so before I talk about the specifics of the ABI and what we're looking at and what we feel is really important to the Android ecosystem, I want to talk a little bit about Android compatibility. So anyone can use the Android open source project to build any kind of application or device that they want. There are people who use it for not only things like point-of-sale terminals, but also things that don't even have screens. And that's totally fine. That's part of the magic of the operating system. There are also people who use the Android operating system and don't want to go through Android compatibility. One of the largest tablet ecosystems from a major e-commerce vendor does not go through Android compatibility. One of the largest virtual reality headsets also doesn't go through it. So we're perfectly fine for people to use the Android operating system to build even even large and thriving ecosystems of other experiences around it. But specific to Android itself, one of the things that we really want to do is try to build an ecosystem where application developers have one target that they can target in terms of an API and a set of interfaces that they know they can rely on. And the device ecosystem can know that if they support that, they have freedom to innovate. And so we can have old applications running on new devices, we can have old devices running new applications, and really that's kind of the magic of the Android ecosystem. That's how we've scaled to over 3 billion devices, over 1,800 device vendors, and many tens of thousands of different devices. And so we basically have a definition document that sort of lays out what does it mean to be Android compatible. There's a whole bunch of stuff about what APIs are available, but also specific to this crowd, what ISAs are available and which ISA features do we expect to be present. And because reading a million-line document and checking it manually would not be very effective, the compatibility test suite is also available in the Android open source project, and so it's a mostly automated set of tests that can verify all of these things. And so if you pass all of these tests and you don't have to go to a separate vendor, you can self-attest. But if you pass all of these tests, your device is considered Android compatible, and then you can use the logo that says made with Android, runs on Android, or similar. Now, there's a bunch of other tests. I mentioned I wasn't going to talk about products, but when we start to talk about what does it mean to have an Android TV or an Android watch or any other Android device, we have a separate set of tests for those. Those aren't as relevant today. You can be Android compatible without running those, but hopefully at some point in the future we'll be able to talk about those. And so I'm happy to get to announce today that we are going to be adding RISC-V as an officially supported ABI to Android and to our compatibility definition document. So you'll see it show up in the coming months in the CDD. After that, we will then link into the part of the documentation where we call out what specific ISA features. So if you look at some of the other ISAs there, we've definitely tried to call out which features are supported and which ones are mandatory here. Right now, what we're looking at on Android is RVA22 with Vector and Vector Crypto. We've been really happy. We've done a deep dive on most of the library and application ecosystem, as well as a lot of the platform components, and we feel that that's a really great profile, and this is a really great set of extensions, and we believe that this is sufficient to have a pretty fantastic experience on Android that's on par with any other devices in the ecosystem. Interestingly, we've ended up not relying on any of the scalar operations or the SIMD or scalar crypto. We've jumped straight to Vector, and it's been interesting in that it's reduced some of the complexity. In a lot of places where our code is optimized today, we have several kinds of SIMD code, and then we have several different variants of Vector code, and it's been really interesting to go through on the RISC-V side and just do one optimization for Vector and see it come out. And it's been interesting watching the rest of the talks, seeing all of the great things that people are doing to take the Vector API and use it in more and more settings for more and more kinds of workloads. And that adaptability, I think, really reduces a lot of the porting burden that we have and the optimization burden when we're looking at activating Android on hopefully a very diverse set of devices in the future. And so speaking of the future, sort of what's coming up next, obviously we're not done. We're gonna get that out. Now you can always follow along. One of the things that we've tried to do is put all of the information about the project and all of the issues that we're tracking, sort of no matter where they show up, whether they're in LLVM, whether they're in the Linux kernel, whether they're just open questions. And we're not having the discussions there. It's pointing to discussions at RVI, at the relevant working groups, at the open source projects. But we try to have one place that centralizes all of them so that we know specifically for the task of bringing up Android on top of RISC-V, what is everything that we're doing. I also want to give a shout out to the Android SIG, which has done fantastic work supporting a broad part of the ecosystem. They have a meeting on Friday as well, so if you're looking for more RISC-V meetings, I recommend attending that one on Friday. You know, the first thing we really need to do is make sure that Vector Crypto lands. It's not fully ratified yet. I have high confidence it looks fantastic, but we've got to make sure all the I's are dotted and T's are crossed here before we can really put that in stone as something that we'll be requiring. We're also really excited. There's a lot of other interesting things sort of on the horizon that we're confident that we can add support for later within Android and still pick up and use. So whether that's improved the ID consistency for improving the performance of our just-in-time compiler, there are a whole bunch of really great security features around shadow stack and the rest that we'd really like to dive in deeper on and see how they get implemented. Hwasan is one of the most effective tools that we have for developer time memory safety checking, and it's been extremely effective in other parts of our ecosystem, and so we'd love to make sure that we have things like pointer masking in order to enable some of those same tools. I've mentioned the atomic support, and no talk would be complete without talking about bfloat 16 and the importance of AI. And that's all I'll say about that. And so we have a bunch of really fun stuff coming over the next few quarters and next year. So in Q3, we're going to have accelerated graphics and the Android runtime. So really taking performance and making it much more palatable to start doing more poking around and more user testing, trying out applications on Android. You're really going to be able to do that at the end of Q3. I also mentioned some of the patches we have available, but are still somewhat in flight. We'll get all of that stuff landed, fingers crossed, in QEMU across the kernel and continue working productively with LLVM and the rest of our upstream maintainers to land all of the optimizations, particularly around vector and some of the other extensions that have just come out. In Q4, we're going to start to have the early builds available so you can test out the native development kit. Now, the native development kit is the component in Android that allows third-party application developers to take their application, press another box, choose another target in Android Studio, and build to target. It will still be only nightly builds available at that point, but this will enable app developers to start seeing, can I build my application? And as part of that, we'll also make it possible for application developers to take that built application in RISC-V and run it on their host machine through dynamic translation or emulation. So we really want to start making it possible for us to move from platform developers and OS developers and device manufacturers to start to get application developers interested in RISC-V and giving us additional feedback on, hey, what's ready, what needs some more work, and how are we doing? And then next year, we want to make those emulators much more readily available for people more than just the early adopters, as well as release a full version of the NDK with RISC-V support. Upstream at RISC-V International, I talked a lot about some of the work on PSABI and our focus there. I think really we're going to be shifting over the coming months to focus on security. There's a lot of things that we rely on in Android that are really come down to isolation. How are we isolating the components of the SoC from one another? How are we isolating workloads within user space from one another, even within an application? How are we doing that isolation right now? And I think there are some really great working groups going on up at RISC-V International that we're already involved in, but we'll continue to get even more involved in. I love seeing all of the innovation in this space, and I realize that there are a lot of technical details to sort out on each of these, and that's a place where we're looking forward to engaging with the community and providing some of the OS vendor feedback as we look at sort of what's feasible and tractable from a hardware perspective as well. And sort of shifting gears a little bit, but not actually too much. When we talk about engagements up at the open source ecosystem, one of the big things that's come up, I think Dom mentioned it really well in his talk earlier this morning, open source is freely available, but it doesn't mean that it's free. And so the question is, particularly as we move to application processor workloads, how are we accelerating and building on all of the great contributions that are already happening in the RISC-V ecosystem? There's already a very rich contributor ecosystem, but in order to get everything fully optimized, CI and CD in place, and really be ready for the launch of commercial products using RISC-V in an application processor, there's a lot more investment needed. And so we formed RISE in order to funnel those investments and coordinate that requirements gathering to really make sure that we know that we are making sure that the open source is successful and at a high level of production quality at the same time that the products are coming to market. And I'm not going to dive in and read everything out here, but we have a variety of focus areas, right? We're really working on making sure that everything that's required for application processors to be successful we understand what the gaps are, and we're funding them. And that's really sort of the working model for RISE, is bringing together the companies who are looking to bring products to market to say, hey, what's the gap? I'm trying to bring this particular product in this form factor. It has needs across these parts of the open source ecosystem. Who's working on that? And sometimes that might mean that the companies have engineers. Some might have more engineers who can work on implementations. Some people might have reviewers. Sometimes we might need to work with other third parties, the reviewers or owners of the particular open source components, maybe at other companies, or they may be volunteers. And so figuring out how do we make sure that we work really well, ensure that the open source projects are well supported, and also that they're not inundated. The last thing we want to do is for a volunteer to get 72 pull requests from Google a day and a stream of comments, right? We want to be mindful of the fact that there are many volunteers in the ecosystem, and how are we not only getting all of the changes in and the optimizations, but how are we doing it in a way that's sustainable and builds a good reputation. So we just launched last week, but the technical steering committee has been going for a while. We've already started coordinating, in particular around a bunch of QEMU features, but I hope this gives you kind of a taste of some of the, like a flavor for what we've been looking at. Andy's, Sci5, Ventana, Revo, several others have already made fantastic contributions that have helped us to nail the pieces that we knew that we needed in order to get the supporting QEMU, as well as in the compilers and tool chains, and we expect to see that accelerate over time. So we're looking for more members here, obviously. Please go ahead and hit riseproject.dev to learn more information about how you can join RISE. And sort of to wrap up here, I hope I managed to keep my word. Like, RISC-V is now a Tier 1 fully supported platform for Android. We are continuing to invest in it. We are continuing to build it out. We have a really great roadmap through the end of the year. And I'd like to thank you all for all of your help, whether it was directly on open source projects or with the evolution of all of the standards and in the working groups that we work on. I'm really excited for this, and I can't wait to see some amazing development boards and test things out in person. Thank you. Oh, no, sorry.
We have time for a couple of questions. If you get close to the mics in the middle of the room, or just raise your hand and you'll get it.
Status of the AOSP, do you believe those can support multiple applications from like automotive, IoT, as well as data center scale devices?
Mm-hmm. So the question is basically around both the flexibility of RISC-V and whether the Android open source project can support them. And so I would say yes, the Android open source project can be configured. You can pass in different compiler flags to compile all the way down to RV64GC. Now, we do not currently support the 32-bit variant of RISC-V, and we're not looking to accept patches for that at this time. But for any 64-bit RISC-V processor, I would expect people to be able to build targeting that device and be able to bring up devices on it.
So then on top of that, does the RISE project intend to serve those multiple application areas as in data center, automotive, and then mobile processor and so forth then?
I think with regards to RISE, I think it depends on what the member companies are investing in and funding. So I don't know if there's anyone representing automotive off the top of my head right now. Obviously Android and the sort of mobile ecosystem are very big. I know that the investigation and readiness for the data center is something I didn't touch on here, but it's a big concern for us as we scale to large computers. There's an even larger open source software stack, and how are we making sure? I think everyone's very excited. How are we getting ahead? I don't have the details for you, but I'd be happy to follow up on the automotive side.
Okay, thank you.
Okay, thank you. Any other question? No, so let's thank the speaker again. Thank you, Lars.
Thank you.